Thank you. Sorry. Go ahead.
We are proud that we Indians are heroes behind the zero. Discovery of zero, present number system, concept of infinity are the greatest contribution of India to the world in the field of mathematics. But today, most of the people are unaware of Indian mathematicians' contribution to algebra. The objective of my today's presentation is to promote awareness about Indian mathematicians' contribution to algebra. One of the most important contribution of them is the discovery of perfect methods to obtain integral solutions of indeterminate equations. So first of all, let us see what are indeterminate equation. Whenever number of unknown variables are more than that of number of independent equations, then there will be infinitely many solutions and equations are said to be indeterminate. Here, any linear first degree indeterminate equation of the form ax minus by equal to c, where a, b and c are constant integers and x and y are unknown variables, it is known as linear Diophantine equation. While second degree quadratic indeterminate equation of the form nx square plus 1 equal to y square is called Varga Prakriti by ancient Indian mathematician. Varg means square and it refers to x square, and Prakriti means nature and it refers to coefficient n. Presently, this equation is known as Pell's equation. Now I present an interesting true story about a very particular quadratic indeterminate equation 61x square plus 1 equal to y square. This is the remarkable example of great historical interest. Famous French mathematician Pierre de Fermat in 1657 AD proposed this equation as a challenge to his fellow mathematicians of the Europe for solution in integers. Several mathematicians participated in this challenge to solve this equation in integers, and this problem interested mathematicians for about 75 years and no one succeeded to solve this equation in integers. Finally, in 1732, renowned Swiss mathematician Leonhard Euler solved this equation and named this equation as Pell's equation. But very surprisingly and coincidentally, the very same equation 61x square plus 1 equal to y square was completely solved by a great Indian mathematician Bhaskaracharya in 1150 AD, 500 centuries earlier. There is no doubt that he has completely solved this equation and got answers x equal to 22 crores 61 lakhs 53,980 and y equal to 1 arab 76 crores 63 lakhs 19,004. He solved this equation by his famous Chakrawal method, and it is given in his book, in his text Bijaganitam. This is the most remarkable contribution of Bhaskaracharya to algebra. Yatha shikha mayuranam naganam manyo yatha tadvad vedang shastranam ganitamurdanistitam. The meaning of this Sanskrit shlok written in Yajurved is as the crest on peacock and jewels on the serpents, the mathematics stays at the head of all the Vedanta Shastras. This is the supreme importance given to mathematics in Vedas by Rishi Lagad in 1000 BC. Mathematics can be found in Indian literature even from the Vedic period. (2000 BC to 800 BC). The first significant mathematical text of Vedic period is Shulva Sutra, composed around 8th century BC, nearly 3000 years back. In Shulva Sutra text named by Vedic scholar Bodhayan, Apastam and Katyayan, mathematical rules for construction of Yajna Bhumika, that is sacrificial altars, are given. Word Shulva means rope which was used to measure length in ancient times. And sutra means formula. For the first time in the world history of mathematics, linear indeterminate equations are discussed in Bodhayan and Apastam Shulva Sutra to construct altars for worship of God. In Bodhayan Shulva Sutra, some examples of simultaneous linear indeterminate equations and their direct answers are given. But the methods of solving indeterminate equations are not given, because Shulva Sutras are books on geometry, not on algebra. This indicates that authors Bodhayan and Apastam were aware of the solution of simultaneous linear indeterminate equations. The method of solving indeterminate equation in integers was systematically discussed for the first time in the world history of mathematics by great Indian mathematician Aryabhatta in 499 AD in his text Aryabhatiyam. So it is with Aryabhatta's contribution that we begin our historical study. Aryabhatta is one of the greatest mathematicians for all times. Aryabhatta's celebrated work Aryabhatiyam text was written in 499 AD. The most significant contribution of Aryabhatta in his text is the method of solving first order indeterminate equation of two unknowns, say x and y, of the type ax minus by equal to c. It is considered as Aryabhatta's most remarkable contribution to mathematics. Aryabhatta given the method of solution of indeterminate equation of first degree in just 2 stanzas in Sanskrit. And the method of solving equation of the type ax minus by equal to c in integers is called Kuttaka. Kuttaka literally means pulverizing or breaking, and the name has been given on account of the process of continued division that is adopted for the solution. I illustrate Aryabhatta's method of solving first degree indeterminate equation with the help of an example 137x plus 10 equal to 60y. First of all, larger of two coefficients, that is 137 and 60, is chosen, and repeated division is performed as an HCF process. As 137 divided by 60 gives quotient 2 and remainder 17. Then we divide 60 by 17 to get quotient 3 and remainder 9. And when 17 is divided by 9 to get quotient 1 and remainder 8. And 9 divided by 8 gives quotient 1 and remainder 1. In this table, the first column is in the form a equal to bq plus r, that is dividend equal to divisor into quotient plus remainder. Second column is for quotients and third column is for remainders. First of all, z, a constant, is to be chosen in such a way that multiplier z on multiplication by last residue, that is ultimate remainder 1, and subtracting constant 10 of the equation from the product, the result should be completely divisible by penultimate remainder 8. So here m equal to 1 and z equal to 18 are final results. And in this here C1 entries are quotients 2, 3, 1, 1. And last and second last row entries are m equal to 1 and z equal to 18. By using IAVM, that is vertically and crosswise method from bottom to top, remaining entries of rightmost column C2 can be obtained. The number 18 of second column is multiplied upward crosswise entry 1, and the product is added to the vertically downward entry 1. Thus 18 into 1 plus 1 is 19. The same process is repeated again and again in column C2. Like 19 into 1 plus 18 equal to 37, and 37 into 3 plus 19 is 130, and 130 into 2 plus 37 is 297. So finally x equal to 130 and y equal to 297 are solutions of the given equation. And noting that 130 is congruent to 10 modulo 60 and 297 is congruent to 23 modulo 137. So we get x equal to 10 and y equal to 23 as simple solutions. And the general solution is x equal to 10 plus 60m and y equal to 23 plus 137m. And with the help of this general solution, infinitely many solutions can be obtained. The method of solving Varga Prakriti nx square plus 1 equal to y square was discussed for the first time in the history of mathematics by Ganak Chakra Chudamani, the jewel in the galaxy of mathematicians. Great Indian mathematician Brahmagupta in 628 AD in his text Brahmasputa Siddhanta. His well-known work and masterpiece, this Brahmasputa Siddhanta, was composed in 628 AD, and its 18th chapter called Kuttaka, which denotes algebra. And this chapter contains method of solving Varga Prakriti nx square plus 1 equal to y square. And this is the most outstanding contribution of Brahmagupta in mathematics. Brahmagupta's lemmas are technically called Samasa Bhavana, means binary composition. Am I audible?
Yes.
Yes, sir. Yes.
You're
Okay.
audible.
Brahmagupta lemmas are called technically Samasa Bhavana. His first lemma is called Tulya Samasa Bhavana, means additive composition of equals. It states that if alpha and beta is solution of equation nx square plus k equal to y square, then 2 alpha beta and n alpha square plus beta square will be the solution of nx square plus k square equal to y square. Brahmagupta's second lemma is called Atulya Samasa Bhavana, means additive composition of unequals. It states that if alpha 1 beta 1 and alpha 2 beta 2 are a solution of Varga Prakriti nx square plus k1 equal to y square and nx square plus k2 equal to y square respectively, then alpha 1 beta 2 plus alpha 2 beta 1 and beta 1 beta 2 plus n alpha 1 alpha 2 be the solution of equation nx square plus k1 k2 equal to y square. Now illustrate Brahmagupta's method of solving Varga Prakriti with the help of an example which is worked out in Brahmasputa Siddhanta. The problem is, what's the number whose square multiplied by 8 and then combined with unity yields a perfect square? So mathematical format of this problem is 8x square plus 1 equal to y square. By Vilokanam, that is by mere observation, 8 into 1 plus 1 equal to 9. So 8 into 1 square plus 1 equal to 3 square. So 1 comma 3 will satisfy the equation. On performing Tulya Samasa Bhavana on 1 comma 3, new solution 6 comma 17 will satisfy x square at x square plus 1 equal to y square. And on performing Atulya Samasa Bhavana on two solutions, alpha 1 beta 1 and alpha 2 beta 2, that is 1 3 and 6 17, a new solution 35 comma 99 obtained. In this manner, infinitely many solutions can be obtained. The only drawback in this method is need of trial solution to start with. Bhaskaracharya was a mathematician par excellence. Bhaskaracharya was most popular among Indian mathematicians. He was born in 1114 AD. Bhaskara's celebrated work Bijaganitam is a treatise on advanced algebra. And most important part of Bhaskara's algebra is exposition of the Indian cyclic method called Chakraval method to solve the indeterminate equation nx square plus 1 equal to y square. Bhaskaracharya improved upon Brahmagupta's method. The handicap of trial solution is ably got over by the remarkable Chakraval method. Now I present famous Chakraval method, a gem of Bhaskara's algebra, to solve nx square plus 1 equal to y square. An auxiliary equation is taken, na square plus k equal to b square, and it is always n into 1 square plus m square minus n equal to m square. So the new solution, or a comma b and 1 comma 1 comma m are solution of these two equations 1 and 2. On performing Brahmagupta's Atulya Samasa Bhavana on these two solutions, a comma b and 1 comma m, a new solution am plus b and na plus bm is obtained, satisfying nx square plus k into m square minus n equal to y square. On putting these values, am plus b and na plus bm in this equation, the equation will become n into m plus b whole square plus k into m square minus n equal to na plus bm whole square. On dividing both sides by k square, the equation so formed is called Bhaskara's equation. Now by Vilokanam, m is chosen in such a manner so that am plus b by k is an integer and modulus of m square minus n, that is absolute value of m square minus n, is minimal. On putting this value of m in Bhaskara's equation, Bhaskara's equation reduces in the form n a1 square plus k1 equal to b1 square. And using a1 b1 k1 instead of a b k in equation 1, the same process is repeated until k equal to 1, 2 or 4 is found. Now Brahmagupta's approach will give the final solution. This is the Chakraval method. To illustrate Chakraval method, I present solution of Fermat's challenge 61x square plus 1 equal to y square, which was worked out in Bhaskara's Bijganitam. Assuming a parallel auxiliary equation of the form 61a square plus k equal to b square, and by Vilokanam, a equal to 1, k equal to 3, b equal to 8 will satisfy an auxiliary equation as 61 into 1 plus 3 equal to 64, that is 8 square. On putting these values in Bhaskara's equation, 61 into m plus 8 by 3 whole square plus m square minus 61 by 3 equal to 61 plus 8m by 3 whole square is obtained. Now we choose value of m in such a way that m plus 8 by 3 is an integer and m square minus 61 by 3 is minimum and numerically small integer. So m will be equal to 7. And on putting this value of m equal to 7 in Bhaskara's equation, the equation so obtained is 61 into 5 square minus 4 equal to 39 square. On dividing both sides by 4, the equation modifies to 61 into 5 by 2 whole square minus 1 equal to 39 by 2 whole square with solution 5 upon 2 as value of x and 39 upon 2 as value of y with k equal to minus 1. And on performing Tulya Samasa Bhavana to 5 upon 2 and 39 upon 2, the new solution 195 upon 2 and 1523 upon 2 will satisfy 61x square plus 1 equal to y square. Next, by performing the Samasa Bhavana between two solutions, that is 195 by 2 and 1523 by 2 and 5 by 2 comma 39 by 2, that is Atulya Samasa Bhavana, a new solution 3805 and 29,718 satisfying 61x square minus 1 equal to y square. And lastly, performing Tulya Samasa Bhavana on 3805 and 29,718, we obtain the solution values of x and y, as value of x is 22 crores 61 lakh 53,980 and value of y is 1 arab 76 crores 63 lakhs 19,049. X having value in 9 digits and y having value in 10 digits. In fact, these are the least integral values of x and y, satisfying the equation 61x square plus 1 equal to y square. And infinitely many solutions can be obtained by repeated applications of Samasa Bhavana. Most celebrated great Indian mathematician of 9th century, Mahaviracharya, discussed very interesting problem of linear indeterminate equations with poetic imagination in his text Ganit Sara Sangra in 850 AD. Here is one problem from Ganit Sara Sangra. Three merchants find a purse lying in the road. One merchant says, if I keep the purse, I shall have twice as much money as the two of you together. Give me the purse and I shall have 3 times as much, said the second merchant. The third merchant said, I shall be much better off than either of you if I keep the purse. I shall have 5 times as much as the two of you together. So how much money is in the purse? How much money does each merchant have? Here is the mathematical format of the problem. P plus x equal to twice y plus z. P plus y equal to thrice x plus z is second equation. P plus z equal to 5 times x plus y. 4 unknown variables are there and 3 equations. So these are simultaneous linear indeterminate equations, where P is the amount in the purse and x, y, z are the respective amount of money of first, second and third merchant. There is no unique solution of this indeterminate equation, but Mahaviracharya ji found the smallest solution of this problem is P equal to 15, x equal to 1, y equal to 3 and z equal to 5. Also, Mahaviracharya claimed that any other integral solution of this problem is multiple of this solution. National Mathematics Day is celebrated every year on December 22 across the nation India to recognize and celebrate the works of Ramanujan. It was on this day in 1887 the Indian mathematical genius Ramanujan was born. Almost coming in the tradition of the ancient Indian mathematicians, Ramanujan is the crowning glory of this great tradition. He was the greatest mathematician of the century and gift from heaven. Ramanujan's equation 2 to the power n minus 7 equal to x square is an example of exponential indeterminate equation. Equation is to be solved in integers, in which one variable appears as an exponent. It is named after great Indian mathematician Srinivas Ramanujan, who conjectured that it has only 5 integer solutions, and these solutions are n equal to 3 and x equal to 1. Second solution is n equal to 4 and x equal to 3. Third solution is n equal to 5, x equal to 5. Fourth solution is n equal to 7, x equal to 11. And fifth solution is n equal to 15 and x equal to 181. These are only 5 solutions. Spiritual teacher, late Swami Shri Bhartikrishna Teerth discovered miraculous Vedic maths in between 1911 and 1918. The basis of Vedic mathematics are 16 one-line sutras and upsutras, which enables us to quickly solve maths problems. And these formulas are easy to learn, fast to use, and less prone to error. Vedic mathematics is very easy, interesting mental maths and fastest mental maths. Vedic mathematics book of Swamiji is 40 chapters, out of which 11 chapters from chapter number 11 to chapter number 20 are on solution of simple and complex algebraic equations. In Vedic maths, there are some special methods for certain pattern of problems and also a general method to solve algebraic equations. I must say very frankly and clearly that Swamiji has not given any method of solving indeterminate equation in the Vedic mathematics book, but he has given very simple and interesting methods of solving miscellaneous linear, quadratic, cubic, biquadratic and higher degree equations, which enable us to give the answer immediately by mere mental arithmetic. But real beauty and effectiveness of Vedic maths cannot be fully appreciated without actually practicing the system. So let's walk into the wonderful world of Vedic mathematics. Simultaneous linear equations are pair of linear equations having two variables, say x and y. And both equations are solved together to get values of x and y. In the CBSE course here in India, we cover this important part of mathematics in class 10th to solve daily life problems. First, I present a special method of Vedic maths for solving simultaneous linear equations. Some simultaneous linear equations which may involve big numbers, but having the certain ratio between the coefficients can be solved easily. This comes under Vedic Math Sutra Anurupaya Shunyamanyata, which means if one is in the ratio, then other one is 0. We take one example. 426x plus 128y equal to 512. And second equation is 792x plus 256y equal to 1024. Here, since ratio of y coefficients is ratio of constant terms, which is 1/2. So the value of other variable x equal to 0 and y equal to 4. Doesn't it look like a magic to give solution of such big equations on mere side?
It is all, I didn't want. This is nice, sir. Choda from like everywhere.
I ask you to please mute yourself.
Wait, you get.
We take one more example to better understand the process. In the second example, ratio of coefficients of x equal to ratio of constant terms, that is 3/4. So the value of other variable, that is y equal to 0 and x equal to 2. And this formula Anurupaya Shunyamanyata can also be extended for solution of linear equations of 3 or more variables. Here is one example. The ratio of x coefficient is 2:3:5, which is equal to ratio of constant terms 4:6:10. Therefore, value of other variables y equal to z equal to 0. And on putting these values of y equal to z equal to 0 in any of the equations, we get x equal to 2. There is another special type of simultaneous linear equations where the x coefficients and the y coefficients are found interchanged. These equations can be solved by using Vedic Maths Sutra, Sankalan Vyavkalanabhyam, means addition and subtraction. And this application can be understood by taking an example. In this example, coefficient of x in the first equation is equal to coefficient of y in the second equation, which is 45, numeral coefficient. And numeral coefficient of y in first equation is coefficient of x in second equation. By addition and by subtraction gives us immediate two equations giving values of x plus y and x minus y. And repetition of same process gives us the value of x equal to 2 and y equal to -1. And the whole work can be done mentally, no matter how big and complex the coefficients may be. We can get the solution by mere addition and subtraction without involvement of long multiplications. We take one more example to better understand the process. Oh, what a problem. And still just add them once and subtract them once to reduce large coefficients. Again, applying Sankalan Vyavkalanabhyam, we get x equal to 2, y equal to 3 as final answer. Amazingly how easy it is. Till now, we have studied two special Vedic math methods for solving simultaneous linear equations in two variables, which are applicable for certain special type of cases only. Lastly, I present general Vedic math method for solving all sort of linear simultaneous equations. We have the general formula applicable to all cases under the Paravarti Yojeta Sutra. The literal meaning of this sutra is transpose and apply. The current method of cross multiplication taught in schools is a good and short method of solving simultaneous linear equations, but the major drawback of this method that many a times students get confused over a positive and negative sign. And Vedic maths method based on Sutra Paravarti Yojeta, that is transpose and apply, enables small mental calculations to give correct answers easily. The Vedic Math Sutra moves in cyclic order. Here is an example of general Vedic math method. The method can be better understood with the help of arrow diagram for solving this example. For calculating the value of numerator of x, we start with y coefficients and cross multiply them with the independent terms in forward direction. And the sign between the two cross products will be minus. And for the result of denominator, we cross multiply the coefficients of variable only starting from y coefficients. And for the numerator of y, we start with independent terms and cross multiply them with coefficients of x in backward direction. And the sign between the cross multiplication results is minus. And denominator of both x and y will be same. The solution of the simultaneous linear equations in two variables by Vedic Math Sutra can also be written in mathematical format like this. And here is an example to show that Paravarti Yojita enables us to give one-line mental method answer. Now I recapitulate the historical travelogue of indeterminate equations. Shulva Sutra. Indeterminate equations were discussed for the first time in the world history of mathematics in Bodhayan and Apastam Shulva Sutra, composed around 800 BC. And these indeterminate equations are called Diophantian equations after the name of ancient Greek mathematician Diophantus of 3rd century AD. But Diophantus was concerned with the determination of rational solution of this equation in his text Arithmetica. Also, his text deals with solving algebraic equations with integer coefficients, for which integer solutions are sought. And the method of solving the linear indeterminate equation in integers was discussed for the first time in the history of mathematics by ancient Indian mathematician Aryabhatta in 499 AD in his text Aryabhatiyam. While the method of solving quadratic indeterminate equation in integers was discussed for the first time in the history of mathematics by great Indian mathematician Brahmagupta in 628 AD in his text Brahmasputa Siddhanta. It is remarkable contribution of Brahmagupta. However, an improved method to solve an equation of the form nx square plus 1 equal to y square was developed by great Bhaskara in 1150 AD in his text Bijagaditam, and this method is called Chakraval. A part of the work Arithmetica of Diophantus was studied by Fermat, and the famous French mathematician Pierre de Fermat in 1657 AD proposed the equation 61x square plus 1 equal to y square for solution in integers as a challenge to his fellow mathematicians. And finally, Fermat's challenged equation 61x square plus 1 equal to y square was completely solved by the renowned Swiss mathematician Leonhard Euler in 1732, and Euler referred to it as Pell's equation. The name given to this equation as Pell's equation is historical error. In 1658, an algebra book was published, which was written with the help of John Pell, and this book contained an example of quadratic indeterminate equation, and it is the only connection between Pell and the equation which has been named after him. This quadratic indeterminate equation is wrongly called as Pell's equation. And most celebrated great Indian mathematician of 9th century Mahaviracharya discussed very interesting problems of linear indeterminate equation with poetic imagination in his text Ganit Saras Sangrah in 850 AD. And in 1913, an exponential indeterminate equation was conjectured by great Indian mathematician Srinivas Ramanujan, which is known as Ramanujan's equation. In 1918, founder of Vedic maths, Shri Bhartikrishna Teerth gave very easy and interesting mental methods to solve miscellaneous algebraic equations. These are references. All the information which I have presented are based on these published works. So let me conclude. It is our misfortune that many links of the past are buried in the sands of time. The remarkable achievement of Aryabhatta, Brahmagupta and Bhaskara II to obtain integral solution of indeterminate equation is beyond all praise. But unfortunately, these amazing discoveries found no favor with some of their successor mathematicians of the world. And this is the tragedy of Indian mathematics. I hope that this presentation lead to a proper appreciation of the greatest contribution of ancient Indian mathematicians, and it should be appropriate to respect Aryabhatta as father of algebra and designate the equation of the form nx square plus 1 equal to y square is the Brahmagupta Bhaskara's equation. Thank you.
Oh, Ravi, thank you so much.
Thank you, Jim.
Swati has had to leave us just a few minutes ago. So I will be wrapping this session up. I must say you've given a very, can you hear me all clearly?
Yes, yes, James.
All right. You've given a fantastic overview of some of the algebraic developments across many centuries based in India, and your presentation is very clear and very interesting as well. We would like to open up to see if anyone has any questions, which you can put into the chat box if you have any questions. Some of the comments coming in are well synchronized presentation. Thank you. Fantastic historical perspective. Badhia explained by Ravi G. I have a question myself, Ravi. You spent a lot of your presentation is about the indeterminate equations. Can you explain to us at all why should anyone bother to try and solve an indeterminate equation? And you mentioned early on in your talk, you mentioned that some of the mathematics being developed in India many centuries ago was in connection with creating an altar of the right size. Does the work that was done on indeterminate equations at all relate to practical application?
Okay, James. The German mathematician Hermann Henkel, 1839 to 1873, well known for his contribution to mathematical analysis and special functions, while making his observations on the Chakraval method, invented by Indians to get integral solution of equation of type nx square plus 1 equal to y square. And there are a lot of application in continued fraction. Some work of Lagrange is also there. After Leonhard Euler, he has also done some work on continued fraction, which is also based on indeterminate equations.
Ah, I see. But as far as you know, not connected with creating altars.
Pardon?
You mentioned earlier on in your talk about the need to design altars for sacrifice and so on. Are indeterminate equations related to this?
Yes. It was in Shulva Sutra actually.
Yeah.
The simultaneous linear indeterminate equations are given in Shulva Sutra, which is the first significant mathematical text of Vedic period, which is composed around 8th century. And mathematical text can be found in Indian literature even from the Vedic period. and they mathematical rules for construction of sacrificial altars are given, and there they use simultaneous linear indeterminate equations, like the altar pertaining a Grahapatya Agni is to be constructed so as to have 5 layers of bricks, one over the other, so as to contain 21 bricks in each layer, and so as to provide an area of 1 square Vyam. These and similar problems will be formed indeterminate equations, simultaneous linear indeterminate equation. I mean to say that Bodhayan, Apastam and Katyayan Vedic scholars were aware of indeterminate equation, but they have not given the method that how to solve this indeterminate equation. They have given only examples of simultaneous linear indeterminate equations along with their answers. I think it is so because the Shulva Sutra is mainly a book on geometry, not on algebra. That is why they not have given the solution of these equation, James.
I see. So that means then that they were using to help with the design of their sacrificial altars, and it is understood that these Indian mathematicians from centuries ago were practical people, that they were like, for example, the astronomers are well known for developing high levels of accuracy with their calculations for practical purposes in astronomical calculations. And this is a feature, and not really describing how, but just giving not describing how the methods work, but just giving the solutions, so to speak. But it is, yeah, it's a recognized trait of the mathematics from classical India.
Yes, absolutely right.
Well, fantastic. Lovely to hear all this, Ravi. Thank you so much. I'll just see if there are any more comments in the chat box. We've got great presentation, sir. Thank you. Nice presentation. So if there are any questions that you'd like to ask, sir, which book, here's a question, sir, which book is good for research work in contribution of ancient Indian mathematics in algebra? Okay,
B.B. Datta and N. Singh, History of Hindu Mathematics from Motilal Banarsi Das House, and also Srinivas Iyengar, The History of Ancient Indian Mathematics, World Press, Calcutta is good book. A.K. Bagh, Mathematics in Ancient and Medieval India. These are good books. T. Saraswati, Amma, of Geometry. It is also a good book.
Okay, perhaps if you could, that was from Ashish Thakkar. Perhaps if you can put in your email address, we can then Ashish will be able to ask you that question by email.
Yes.
There it is.
You can see my email ID.
Yes.
Email
Yes. Thank you.
That's
great. Rasomni. Okay. Well, thank you. Another comment here. Can we use yajna instead of sacrifice? Yajna.
Yes,
I see.
Yes.
Listening terms does not sound right. Okay, in Sanskrit, yes, it is yajna.
Yes, it is more correct word, I think.
Yeah, absolutely.
Bhumika is more correct as compared to that of sacrificial altar.
Absolutely, yes. Of course, when Sanskrit is translated into English, you always lose some of the meaning.
Yes.
Yeah, yes, that's right. Well, thank you, Ravi. Thank you so much. And that was a really good talk. And we will, well, it's been recorded, and we will put this up into our YouTube channel so that other people can watch it as well. So thank you very, very much indeed. That's
thank you so
wonderful. All right, we'll draw it to a close now. Thank you.
Thank you.